In the previous class, in the previous lectures, we discussed about magnetic circuits. We discussed about magnetic circuits and electromagnetism. We discussed about magnetic circuits and electromagnetism, and I told you that electromagnetism is the basic principle behind transformers and electrical machines in the electrical circuits. So in today's class, we will be studying transformers. So what are transformers? Transformers are two terminal. Basically, there can be multiple terminals, but we are considering two terminal device. Transformers are two terminal device which has primary and secondary winding, which is used to step up and step down the voltage. Step up and step down the electrical voltage. We know that power is equal to voltage into current. We know that power is equal to voltage into current. That means if you are increasing the voltage, current will reduce. If you are keeping the constant power, then if you are increasing the voltage, the current will reduce, or if you are decreasing the voltage, current will increase. Therefore, in an electrical transmission line, we know that the power loss, P loss, is equal to I square into R. Okay, where R is the resistance of the line, and we know that as the current, from this one we can see that as the current increases, losses increases. In a system, we try to reduce the losses as much as possible in order to increase the efficiency of the system. Therefore, we need to reduce the I square R loss. Okay, I square R loss can be reduced by reducing the current through the conductor. In order to reduce the current, we can increase the voltage. That is achieved by using transformers. So let us and moreover, if the current is less, the cable size required to transmit that current is also less. If the current is less, the size of the cable required to transmit that current is also less. So therefore, for a small current, we will use the wires which are thinner. For a high current, wherever the application is high, we use high current. We use the thick wires. For example, in your houses, you can see that there is high ampere switchboards which will be connected, which are connected to some particular devices. For example, AC will be connected to different switchboard when compared to that your laptop or your phone charger. That means because it needs higher current. So higher current will need the thicker wire, thus increasing the cost. So if you reduce the current, the cost of the wire will also reduce. That the current is reduced by increasing the voltage by using transformers. So let us say we are generating the power at 11 kilovolt. Then we will step up and transmit it at 400 kilovolt. We will step up the voltage, then we will transmit it at 400 kilovolts. Then again, in the distributing stations, we will step it down to 11 kilovolt. Then this will be transmitted to your home. There will be a transformer in your home which will step down again from 11 kilovolt to 440 or 220 to 30 kilovolt, depending on three phase or single phase supply. So this is one of the advantages of benefits of transformers. Another benefit is, I told you in the previous class, it provides isolation. As I have told, these two terminals, primary and secondary terminals of the transformer, is not physically connected. They are electrically isolated. Physically, they are not physically connected. There is no electrical connection between them. There is only magnetically they are connected. The flux is linking between these two terminals. Therefore, fault occurring here will not be transmitted to this side, or the fault occurring here will not be transmitted to this side. So there are two basic advantages, that is step down and step down. It is one, and the other one is isolation. It provides isolation. So let us understand ideal two-winding transformers. So a transformer consists of two coils. Wound around its two legs of the magnetic core. This is the magnetic core. These two are the coils. This is a primary coil. This is a secondary coil. So the power is transferred from primary to the secondary by the magnetic field induced by the magnetic flux or magnetic field induced in the core. Okay. Therefore, as you can see here, the primary is connected to the source and the secondary is connected. In this case, we are assuming that primary is connected to the source and secondary is connected to the load. So when we are considering ideal transformer, we will assume few things, which is not the case in a real transformer. So we will assume that primary and secondary windings has no resistance, whereas in the real case, primary will have resistance. Any conductor will have its resistance, so there will be a losses, and therefore even the coil connected across the transformer will also have resistance. But for the sake of ideal transformer, we are considering that primary and secondary winding has no resistance. We will consider that the flux produced in the primary, all the flux produced by the primary winding is linking with the secondary winding. We know that is not the case. As I have discussed you in the previous class, there will be flux, some flux linking with the air that we call as leakage flux. In a ideal transformer, we will consider that all the flux generated by the primary will be linking with the secondary coil. And we will consider that the permeability of the iron is infinitely large. That means a small current or negligible current is required to establish a flux, but that is not the case, which I have told you. You need much larger current. There will be the flux density. I have discussed BH curve. The flux intensity or current should be increased in order to produce the reasonable amount of flux. This we have discussed. So we will also assume that the core losses comprising of eddy current and hysteresis losses does not exist in an ideal transformer. In order to understand the transformer, we are basically neglecting the core losses. We are neglecting the losses of the windings. We are considering there is no leakage flux, and we are considering that the permeability of the material is infinite. Therefore, a minimum current is required to establish the flux. So let us analyze a ideal transformer. So let us say that the alternating flux link both secondary and primary. Let us consider the flux is phi m sin omega t, where phi m is the magnitude of the flux, where phi m is the magnitude of the flux. We know that E is equal to the EMF induced, E is equal to minus n d phi by dt. That is directly proportional to the number of turns in the primary. EMF induced in the primary coil is directly proportional to the number of turns in the primary, and it is also directly proportional to the rate of change of flux. This we have discussed in the previous class. This includes laws of electromagnetism and also Lenz's law. Okay, Faraday's law and Lenz's law. So we have discussed this in the previous class. The flux induced can be written as omega n1 phi m cos omega t. That is 2 pi f n1 phi m sin omega t minus pi by 2. Okay, sin omega t minus pi by 2. Therefore, the EMF induced will have a phase shift of 90 degree between the flux and the induced EMF. So the RMS value of the flux can be written as 4.44 F N1 phi m. This we have discussed AC operation of the magnetic circuit, AC operation of them in the previous classes. We have derived this equation, and we know that induced EMF E1 is equal to 4.44 F N1 phi m, where F is the frequency of the AC voltage and N1 is the number of turns in the primary, and phi m is the magnitude of the flux. Similarly, RMS value of the induced voltage E2 is equal to 4.44 F N2 phi m. Again, this is the frequency, this is the number of turns in the secondary side, this is the magnitude of the flux. This is the magnitude of the flux. So we can write that E1 is equal to 4.44 F N1 phi m, and E2 is equal to 4.44 F N2 phi 2 or phi m. Phi m is the phi flux, because flux linking both primary and secondary is the same. Therefore, we can write it as phi m, where E1 is the EMF induced in the primary coil and E2 is the EMF induced in the secondary coil. So let us see what is turns ratio and the phasor diagram of the transformer. So we know that V1 and V2 are the terminal voltage, and E1 and E2 are the induced voltages. So this is a transformer, this is core, this is a transformer, this is core. So basically, induced voltage, the voltage across the primary coil induced is E1. So the applied voltage across the primary coil is V1. Applied voltage across the primary coil is V1. Okay, so induced voltage across the secondary coil is E2, induced voltage across the secondary coil is V2, and the voltage across the load, secondary load, is V2. Okay, so if you, so we know that V1 is equal to negative of E1 because of Lenz's law, the induced voltage will be opposing the source caused it, therefore V1 is equal to minus of E1. But however, the voltage across the secondary E2 is the induced voltage, which will be equal to applied voltage because there is no source here, therefore the induced voltage E2 is equal to V2. So we can write this under this condition. We can write V1 by V1 by V2, which is equal to E1 by E2. If we submit the equations which we have discussed in the previous class, we can understand that even V1 by all these things are same. 4.44 F phi m, 4.44 F phi m, all these things are same. Therefore the only different things is N1 by N2. The only different thing is N1 by N2. So we can write it as N1 by N2. N1 by N2. So which is equal to A, which is a turns ratio. So you can understand from this one, V1 by V2 is equal to N1 by N2. V1 by V2 is equal to N1 by N2. Okay. So we can write it as V1 by V1 N2 is equal to V2 N1. V1 N2 is equal to V2 N1. From this one, this equation, you can understand that if the number of turns in the primary and secondary are same, then if the number of turns in the primary or secondary are same, then V1 is equal to V2. It's just the voltage, applied voltage will be reflected across the secondary. Applied voltage across the primary terminal of the transformer will be reflected across the secondary terminal of the transformer. If N1 is greater than that of N2, that means V1 will be higher, V1 will be higher, V2 will be lower. That means it's a step down transformer. If N2 is greater than that of the number of turns in the secondary is greater than that of the N1, then V2 will be more, V1 will be less. Therefore, it's a step up transformer. The voltage is being stepped up, or in this case, voltage is being stepped down. Therefore, it's a step up transformer. If N2 is greater than that of the N1, then that means it's a step up transformer. Okay, so in this case we can see that we can when there is no load connected across V2, we can draw the phasor diagram as this. We know that the induced voltage is phase shifted by an angle of 90 degree. This we saw here, induced voltage is phase shifted by an angle of 90 degree to the flux. Therefore V1 is equal to negative of, V1 is phase shifted by an angle of 90 degree, this is 90 degree. V1 is equal to negative of E1 is equal to negative of V1. So if this is V1, this will be E1. If this is, so I will write it here. This is flux. This is V1, and E1 will be negative of that of V1. Therefore, this is E1. So the voltage, this is not V2. This should be V2. So the V2 is also equal to this is E2, which is also equal to V2. This is E2, which is also equal to V2. This is E2, which is also equal to V2. So this is the phasor diagram of the transformer. Now we understood that there will be an applied voltage V1, there will be an induced voltage E1, there will be a induced voltage across the secondary of the transformer, which is E2, there will be a terminal voltage across the secondary, which is V2. So we know that V1 and E1 both are in the different direction because of Lenz's law. However, E2 will be equal to V2 because there is no source connected across the secondary of the terminal, and V1 by V2 is equal to E1 by V2, which is equal to N1 by N2, which we call it as A turns ratio of the transformer. So further we will discuss in the next lecture.